Welcome to The Explainer. Today, we're going to talk about something pretty wild, how invisible computer code can cause very real, very physical destruction to our world's most critical infrastructure.
And look, this isn't a plot from some sci-fi movie. It has already happened, and it reveals a terrifying new kind of vulnerability, where digital attack translates directly into mechanical failure.
So how is that even possible? Well, to really get it, we have to look back at the classic example, the one that really put this on the map, a sophisticated piece of malware known as Stuxnet.
Okay, so Stuxnet was just brilliant, in a terrifying way. It was a four-stage attack. First, it snuck into a secure network. Then, it hunted for specific industrial controllers. From there, it started secretly manipulating the centrifuges, forcing them to spin at destructive speeds. And here's the craziest part. It completely deceived the operators by feeding them false data, making it look like everything was running normally, while the machines were literally tearing themselves apart.
Now, the systems Stuxnet attacked weren't your typical office computers. No, they were part of this invisible backbone of our industrial world called operational technology, or OT for short.
Just think of OT as the digital nervous system that runs, well, everything. Power plants, water treatment facilities, factories, pipelines, you name it. It's the code that actually interacts with the physical world, the code that flips the switches and turns the gears. And this slide right here shows a fundamental difference in design. You see, information technology, or IT, that's built to protect data. Confidentiality is king. But OT, it was always designed for physical safety and non-stop operation. It usually lived in these isolated, air-gapped environments, where cybersecurity just wasn't the top priority.
For decades, that physical isolation was their security. But then came the push for efficiency, for more data, and we started connecting these systems to the internet. And what that did was create a massive and often undefended digital doorway straight into our most critical infrastructure.
And incredibly, tools like the search engine Shodan make finding these vulnerable systems as easy as a Google search. Anyone, from a security researcher to a bad guy, can use it to find specific industrial equipment connected to the internet. It's basically a map of potential targets. So, the crucial point is, this number, over 65,000, that's a conservative estimate of industrial systems plugged directly into the internet. And a lot of them don't require any authentication at all to access them. In way too many cases, the front door is just wide open. And these vulnerabilities, they aren't always some super sophisticated secret exploit. A lot of the time, it's just basic security neglect. We're talking software that hasn't been updated in years, weak passwords, or no real separation between the office network and the factory floor, which gives attackers an easy path to take control.
But this creates a huge conflict, right? Because we are connecting these systems for really powerful reasons. We're using things like artificial intelligence and big data to kickstart a whole new era of industrial efficiency.
I mean, industries are using AI to analyze real-time data to predict when equipment might fail, to optimize processes, and to improve safety. This predictive power promises a smarter, more efficient, and ultimately safer industrial future. And here's the tension. The same connectivity that lets us use AI is often layered onto a really fragile foundation. As we've seen in real-world incidents, from Ukraine's power grid to a German steel mill, the consequences are no longer just digital. They're measured in broken steel, grid instability, and uncontrolled shutdowns. So, how do we secure a world where digital threats have physical consequences? The solution isn't just about better technology, it's about building a human firewall. Of course, we absolutely need advanced technical defenses. This means building systems that can spot when a physical process is acting strangely, even if the digital signals look normal. It also means strengthening our safety systems and creating emergency plans that get both cybersecurity experts and engineers in the same room. But the ultimate defense is a new generation of professionals who speak both languages, engineering and cybersecurity. They need that industrial know-how combined with AI literacy and a deep understanding of cybersecurity. These are the people who can bridge the gap between IT, OT, and engineering, creating a resilient, knowledgeable human defense layer.
And this is the fundamental challenge we're all facing. As we build a smarter world, are we also building a more fragile one? Securing our future isn't just about protecting data anymore. It's about protecting reality itself. Thanks for joining this explainer.